In this lecture, we'll go over the semantics and code generation phases of the compiler. As we alluded to in the last lecture, just because we have a statement that's grammatically correct doesn't mean it's going to make any sense. Let me give you an example of a grammar where we would have this case. Let's say we have a sentence and it's defined as a noun and a verb and ends with a period. And then a noun would either be dogs or bees, and then our verb would either be bite or bark. So the language is actually defined by a couple sentences. So let's take a look at one such sentence. Let's say we have bees bark. Well, if we were to follow the parse tree, bees is a noun and bark is a verb, and then we have a period at the end. So this is grammatically correct just based on the grammar that we have. But when's the last time you've heard of a bee barking? It just doesn't make any sense. I haven't heard about any barking bees. I don't think you have either. So it's grammatically correct, but it just doesn't make any sense. The next phase of translation is called the semantic analysis. And this just simply involves analyzing the meaning of the tokens, and it tries to understand the actions that the tokens are trying to perform. Now, if the statements are meaningless, then they're just basically rejected. So it doesn't make any sense. So they just reject those statements that don't make any sense. But if all of the statements do make sense, then the compiler will translate it into machine language. Now you might think, this is easy to do for English language sentences. They may be syntactically correct but semantically meaningless. But what about these meaningless statements in a high-level programming language? Well, let's take a look at an example of something like sum equals a plus b with a semicolon. Now, this is going to be correct syntactically, but what about the meaning part behind it? Well, if a and b are integers, then this makes sense. You take an integer, you add another integer, and you get an integer. That's fine. But if we have something like a is a character and b is a double, then this doesn't make sense. You can't take a character and add a double and get like an integer as a result. So this is where we're talking about things making sense. And maybe I don't think I've mentioned double before yet in this class. In case I haven't, which I don't think I have, double just simply means it's a number that can hold decimal places as well. There's more memory that's allocated to store a larger value in terms of including like decimal places in the number. So we can't take a character and then add a decimal to it and get like an integer. That doesn't make any sense. So that's what we're getting at here. So what we saw with that example is if we're going to check the meaning, we need to check the data types that are associated with the statements. So if we're going to check for a semantic error, then the compiler must first look at the parse tree just to see whether there is a branch that looks like that particular statement. So it has to check that the branch does exist. And if there is such a branch, then the compiler must examine the data types of the parts of that branch just to make sure that they actually make sense. So they'll look at the data types that are associated with each non-terminal in that branch. And this is done by examining what's called the semantic record. So this type of information is what we call the semantic records. And so they are associated with each non-terminal symbol in the grammar. And so a semantic record is basically a data structure that stores information about a non-terminal. So this will include like the name of the object and the data type. So for example, we may have a non-terminal called variable, and it might have been constructed from the actual character named ch. So here ch would be the name of the variable, and this relationship would be represented by a link between the non-terminal variable and a semantic record that contains the name ch and its data type character or char or char, however you pronounce it, but I usually just say char. So let's use a plus b as our example, and let's go over how we would do this. So we first need to check the parse tree just to make sure that we find the respective branch. If it's not even there, then we got an error. So assuming that there is a branch in the parse tree, we would take a look at the semantic records for each part of the parse tree. So each non-terminal in there has a semantic record that includes the name and the data type associated with that non-terminal. So then we would check if the expression of the a plus b with the respective data types makes sense. So making sure if we have two integers and we're adding them up, does that make sense? Or do we have like a character and trying to add like a double or an int with that? So we check the data types to make sure that this is valid. And if it is valid, then we would just simply generate the machine code. So let's say this is our parse tree for a plus b, or at least a branch of it. So this is saying that we have these two expression non-terminals, and they have integer values named a and b. So we have the semantic record for a over here, and we have the semantic record for b over here. So the result of this is an expression non-terminal that's stored in the integer variable temp. So we get the semantic record over here with that. Now the name temp is picked by the compiler. Now because the addition is well defined for integers, this operation makes perfect sense. So the compiler can generate machine language instructions to carry out this addition. Now let's suppose this is our parse tree instead of what we had before. So here the compiler is going to determine that this is not a meaningful operation because addition is not defined between a real number, which we have a double over here, and a character over here. So the compiler is going to reject this parse tree for semantic rather than syntactical reasons.